Hello, this is the second of 4 videos on momentum and conservation of momentum. In this video, we will talk about impulse. If we rearrange the force equation and solve for change in momentum, we see that F equals m delta V over delta t. We multiply both sides by t, we get F times delta t is equal to m delta V, or the change in momentum. This quantity, F times t, or the change in momentum, is also called the impulse, and the symbol is an I. Its units are newtons times seconds, which are also the units of momentum, kilogram times a meter per second. Impulse is the change in momentum. It can be found by finding the change in momentum or by multiplying the force times the time over which the force is applied to change the momentum. It's a vector, just like change in momentum, and its direction is the same as the force acting on the object. So, we can calculate the impulse 2 different ways. We can either multiply the force times the time over which it's applied, or we can multiply and find m times delta V. Also remember this relationship between impulse and time and force is interesting. If I look at the original equation, the change in momentum over the change in time is equal to the force needed to change the momentum. That means that time over which the force is applied is inversely related to the force. So, think about it. If I want to stop a car that's going 60 miles an hour, if the car rams into a wall, it has to stop very suddenly. Because it's traveling at 60 miles per hour, it has a lot of inertia. And you have to stop that inertia almost instantaneously. And in order to do that, you would have to apply a super high force to do that, to change its momentum speed from 60 to 0 over a very short time, just a few seconds. But if the truck runs into a big cushiony pillow or a haystack or something that's very soft and has some give to it, not as much force is going to be required to stop it. And coincidentally, the car's not going to be as damaged. So the longer the amount of time the change occurs in, the less force needed to get the change to occur. This is why gymnasts use mats and they bend their knees when they land. If they did not use mats, which have that cushion, and they didn't bend their knees, then when they hit the floor after doing some kind of, somersault or stunt, they would hit rapidly and they'd have to come to a stop very quickly, which means there'd have to be a huge force on their joints, which would cause damage. This is also why a baseball player catches the ball but moves with it when he catches it. He never just holds his hand out, in front and hold rigidly. He catches it and he moves with it, because if he moves with it, it doesn't take as much force to actually stop it from moving, and it doesn't hurt his hand. It's also the reason why gloves are padded, right? To lengthen the amount of time that the change occurs in, reducing the amount of force. So, the other thing is that a large force for a short period of time or a small force for a longer period of time can produce the same change in momentum. So, let's consider a 1 kilogram ball that hits the floor at 20 meters per second. 1 millisecond later, it rebounds at a speed of 20 meters per second. So it's like our bear example from before. The initial momentum will be 1 kilogram times negative 20 meters per second because it's moving downward. That gives us negative 20 units of momentum. The final momentum would be 1 kilogram times positive 20 meters per second. It's positive because he's moving upward now, so now he has a positive 20 units of momentum. The change in momentum would be the final minus the initial, positive 20 minus negative 20. So there would be a change of 40 units of momentum in the positive direction, because the force acting on it is upward. That's why he bounces up. The impulse is equivalent to the change, so it's also 40 kilograms meters per second. but the force is the rate at which the impulse occurs. 40 divided by 0.001 seconds gives us 40,000 newtons in the other direction. What about our classic example of a bug hitting a windshield of a moving car? Now we know the bug dies. We hope the bug dies. If the bug didn't die and the car died, that would be a weird world. Which experiences degraded force? Well, we know from Newton's third law, they're going to impact with an equal and opposite amount of force. We also know that they're going to hit each other for the same amount of time. So that means that the impulse is the same. Impulse is force times time. If the force is the same, if the time is the same, they have the same amount of impulse, just in opposite directions. Same thing as a force. Same force, opposite directions. And if those two are true, then they'll have the same change in momentum. So the bug changes its momentum the same amount the car changes its momentum. But the problem is that that bug doesn't weigh very much at all. It has a very small mass. And because it has a small mass, it appears to have a lot bigger change in momentum because it actually stops, right? It slats. It has a bigger deceleration. The rate at which the velocity is changing is bigger than that of the car, we hope. But that doesn't mean that the momentum change is different. Because remember, momentum and acceleration are two different things.